What's up, guys? In this video, I'm going to be going over a complete guide to system design for a complete beginner. We're going to try to do this pretty short. If you don't know who I am, I've read Designing Data-Intensive Applications. I've read Alex Hsu's Volume 1 and Volume 2. And I've also read like this little book over here, Hacking the System Design Interview. And so what I'm going to do is summarize those books. I'm going to give you a roadmap. Two, I'm going to summarize Don Martin's System Design Primer, which is an incredible resource for someone who's like looking to start system design. So let's get into this. So number one is you want to hop over to this System Design Primer. If you don't know, like this GitHub repo, I'll try to link it in the description. And this is kind of based off, like, even before going into this, let's go over what the roadmap is, right? So the roadmap is based off of this GitHub repo, System Design Fight Club. He is a Apple senior engineer doing staff interviews for in this terrible job market we find ourselves in 2024. But he has an amazing resource, which is a roadmap. So like if you are a beginner, you're a complete beginner, you've never done system design before, you've never studied it before, right? The best thing you're going to want to start with is this Don Martin System Design Primer. And this for mid-level will take you to a level where you're doing decent. You will do okay in your interviews. You will understand them. You'll be able to do it. And the only thing you're really missing is the practical application, applied problems that you need to solve. And then you can probably get away with like just this one and then this one. If you got lucky, like you'll fail interviews, but you'll get lucky. If you want to kill it, you do Don Martin, do this one, then System Design Volume 1, then you do Volume 2, and then maybe do Designing Data-Intensive Applications for mid-level, right? And so we can even go into his resources here. You don't actually even need to read the books. There's a lot of YouTubers that actually do it, like myself. I got, 5,000 subscribers at the time of recording this, so a lot of bad YouTubers, low quality ones who are summarizing these exact books. You can watch those. There's even some good ones too you can watch. These aren't system design at all, though. I don't know why these are mentioned here. Alex Hsu's by ByteGo channel is really the only one, and that can take you there too. But you'll go through these, finish them, take your notes, understand it, learn something, and you'll be good for mid-level. And then for upper end, right, you should read Database Internals, and you should read Understanding Distributed Systems, and then the Google SRE book. DDIA, of course. Real academic papers too can help you. Some more white papers. And there's like just pure academic resources that like no YouTuber really wants to touch, the academic ones. This is good, right? So this is the roadmap for you to like get into system design to pass your interview and then hopefully make, a lot more money at your new job. So let's go into actually like the first guide, which is System Design Primer. So I'm going to walk through this. To my knowledge, nobody's actually walked through this entire book or this guide, and so I'm going to go through it. So he starts here. I don't know why this looks like this. Honestly, this is pretty ugly. This should be taken out. This doesn't have any context, no meaning, no title. So the motivation, he describes why he's doing it. It's just to help people. TLDR, just to help people. He's got some Anki flashcards, some coding deck, system design topics. And here are all the system design topics. We have the study guide. For interviews, do I need to know everything here? Right. This is going to depend. I mean, he's got his own thoughts or whatever. But as I said, if you finish this, like you're fine for interviews. Like you'll fail some interviews for sure, but you'll do fine. So for system design interviews, right? Like again, if you're a beginner, this is the video for you. For system design interviews, we want to follow this guide, which is one, we want to ask clarifying questions, right? Ask clarifying questions, figure out who's using it, what is using it, what does it do, what are the edge cases. All those questions need to be asked at the start so that you can gather requirements, right? So this is going to be gather requirements, scope the problem, see the scale. And if you look at Alex Hsu's book, he does a good job of giving you examples of these. These questions aren't that good at all. These aren't even examples. These are just questions. Then you want to draw out a super high level diagram. And then after that, you want to actually deep dive into parts. So what you'll typically do is you can talk about your own things that you want to talk about for the system, or you can ask your interviewer or ask the interviewer, hey, what would you like me to talk about? What would you like me to focus on? I said I'm going to use a database. Do you want me to deep dive into which database, right? These are questions that you can do. He gives some good examples here, right? So if you're doing a URL shortening service, like how are we going to hash it? Are we going to use MD5 and base62? Are we going to handle, how are we going to handle hash collisions? How are we going to handle, do we do SQL, no SQL, database schema, right? This is the part, this is the meat of a system design interview, where you'll spend 5 minutes on this, 5 minutes gathering requirements, 5 minutes drawing a high level diagram, and then you'll spend like the rest of the interview answering questions and on the components, on deep dives for the components. Then we have scale the design. So then you can add in like some little features, load balancing, horizontal scaling, caching, database sharding. Usually the interviewer will call you out immediately for a load balancer, but yeah. There's some things called back of envelope calculations. I don't know if he has any things here for this. I've actually never seen this resource. This is a pretty bad resource, I would say, if it's not. Yeah, it seems a little stupid to me. Okay, yeah, it seems a little stupid. This does not seem like a good one. And I say this isn't good because, like, there's easy ways to do these. This is just like the math part of it, so it's not even the easy way. It's just the math. But there's resources here. We're gonna skip over this because it's just not relevant for this for beginners. I mean, it's relevant for beginners, right? If you're trying to pass a mid-level interview, like they may ask you to do this if it's more than 1 hour. But this is something that's not too hard to calculate. Like it's math, and most programmers I think know math. Maybe that's a bad assumption on my part though. So here's some example problems: design Mint, designing a social network, design a cache, key value store, design a system that scales. Right, we got a lot of these, man. We'll always skip through them. These don't matter. So here's the meat of it. So these are the system design topics. This is the things that you need to know, and they aren't really going to be that bad. So he says, okay, you should read the scalability lecture, which just covers like vertical scaling, horizontal scaling, caching, load balancing, database replication. So let's talk about these, right? Let's go over these. Let's say you don't want to watch this 1 hour, 2 hour video. I'm going to try to explain these very quickly. Vertical scaling is the idea that, so one is that the whole goal of system design is to build scalable applications. It's that we want to build things that like somebody that has, 100 billion users can do. Something that has 100 million users, 100 billion users, 100, what's more than a billion? 100 trillion users. That's the point of this. And it actually ends up being the case that it's very simple to build a system that only works with one user because you just have one server and you just take in API requests. And the companies that are hiring for these, they have millions of users. You all know their names. You use their apps. You use Facebook. You use Google. And they want scaling. So there's two types of scaling. There's vertical and horizontal. Vertical is the easier one. Vertical means that you just add in, wait, where's actually the meme? It was basically like these little doggies. They were like these little cute dogs and they had like battle armor. But like you had one, this was vertical scaling. It was like a big dog with like some big battle armor. And then the horizontal scaling was like little miniature ones like this. But that's actually like in reference, right? So vertical scaling is the idea you build out your PC, you deck out your PC, get that GTX or what is it, RTX like 3050 Ti. And then the other one is like you make little bitty PCs. That is like directly what's happening with vertical and horizontal. So this is vertical. You max out one PC, one server as much as you can, but it's limited to the specifications of our time. And then this one is not limited by that, but it's just more complicated to handle. So that's vertical and horizontal scaling. Caching, again, super important. This makes lives easier. So like obviously this is what horizontal is, what allows us to scale to billions of users, and vertical is, it's just more convenient, probably like what everybody would think about. But then there's caching too, which helps us scale. So this is the idea that like you can take tons of requests, and then instead of having, you can take tons of requests that go through and you can just cache and save the values that happen, right? So for example, if a user always says, I want to book a like Tesla call or something in like SF or something, I don't know. If somebody always wants to book a Tesla call, like they just always want to like book a Tesla call, what you can do is just say like, okay, instead of writing out all the Tesla information, so like, oh, I need like Tesla, like it's like this model and like it's like this name, and I don't know, man. I don't know. You have all this data, right? And instead of filling out all the time, every single time for all like 1,000 of these, you just save it, and you just say like, oh, well, it's a Tesla. Okay, well, let's just save it and just grab the data. And we can get that in O of 1. Again, if you don't know what a cache is, it has a hashing algorithm. And if you don't know what a cache is, go back to data structure algorithms. You need to do more Leetcode problems. 2, if you do know, then yeah, it's going to just be O of 1. And that way you can save this data. So it's the idea of like caching data, and you can do this for Tesla call or whatever. You could do this for looking up someone's Facebook picture. Maybe everybody goes to Beyonce's like picture. I don't know, or maybe everybody goes to like Beyonce or Shakira's picture. And so instead of like loading all the data again and fetching it from the database, instead of going into the database every time, what we do is we just say, oh, hey, we have like a little mini database, which is our cache, and we just send the traffic there instead. And then this little thing is already going to have like that. So we don't need to scan through. Again, we don't need to do O of n. We just go through O of 1. O of 1. So that is this idea of caching. Again, if you're, yeah, that's like it for like beginners and for that. And he'll go into this more, load balancing. So load balancing is this idea that if we have billions and billions, if we have billions and billions of people like trying to go to this website, so they all want to go visit the website, we can like slow them down or like route them. Very akin to like creating a like roads on a highway where we just like split it. So we branch out here, send one person to here to be serviced, one person to here to be serviced. And there's a lot of load balancers. I think one popular one is Nginx, right? This is a load balancer. And it's what it does is it's routing the traffic. So traffic goes through, there's like a massive amount of it, but then we start like splitting it out and branching it out like that. Kind of like roads on a highway where you've got like one road and there's tons of traffic that's trying to get through, but you can't service all of that traffic. You can split it out and reroute it to other servers. Database replication is this idea of having multiple databases so that your data is good. So you have one database, two database, three database. Now, if one goes down, we have copies of it. It's good to have copies of data. And then data partitioning, which is the idea of having a database that's entirely dedicated to like one type of data. So for example, if this was like Beyonce, or we can have like our Beyonce database, and then we can have like our Shakira database. And then now we can actually store these. Like normally you would just say like, oh, okay, well, I'm going to keep, Shakira and Beyonce's profile is on the same database, but like you can split these out and split them out. In the sense of like a hotel, it would be that you have a database for every single hotel. And you can do these by like using sharding, partitioning, and things like that. And again, I'm sure you don't know what sharding is, but that's okay. I'm sure it'll be covered in this article. And then there's the scalability article he links. Yeah, again, same stuff that I've said, right? Is if you want this, so you have databases, you have caches, I didn't go over async, but that doesn't matter really. So then we look at performance versus scalability. So as you increase scalability, you're going to increase complexity, which will generally reduce performance. So things will probably just go slower. It just takes more time, unfortunately. But there is performance, and then there's actual like numbers, like, right? So performance is this slow for a single user. Scalability is slow, but it can't handle load. Then we have latency versus throughput. Latency is how long it takes something to occur. Throughput is how many people can kind of get through that. So how many requests can get through typically, right? So if it takes 1 hour because your internet sucks, that's going to be high latency. If you can do it in 1 millisecond, but you can only handle one thing at a time, that's like a throughput issue. Like your road isn't big enough. Availability versus consistency. So these are two trade-offs again that we're going to be making typically, right? It's either always available or always highly consistent or whatever. Like there's trade-offs between these. Just and by available we mean that like it's actually active, everybody can use it. Consistency meaning that like the data is like stale, like sometimes it's going to take a while for the data to pick up. So, and this is CAP theorem, which is a very popular theorem for doing these. Honestly, partition tolerance is like pretty cringe part of it. Like if you're building a distributed system, you always want partition tolerance. So the CAP theorem states that like you can only choose one of them. You can only choose two. Pick two. You have these three options, pick two. But like in a distributed system, you always want this one. So you really can only pick between these two. Consistency patterns. So consistency is a super weird term. If you're a beginner at this, we'll talk about for mid-level people. It's always going to be like weak or eventual consistency, which is just that like the data gets there eventually, which is doesn't really matter. Like that is like such a useless term. The data gets there eventually. That has no meaning whatsoever. Like that's not actually like a hard number. But he says here it's typically in milliseconds. But again, it's super weird, man. Super weird. Because does that mean this one's nanoseconds? Like, there's no actual numbers. These terms don't mean anything, and they depending on who you're talking to. And again, this is a quote directly from Kleppmann's book, Designing Data-Intensive Applications. So if you guys want to read that, you guys can go ahead. But we have availability patterns. So this is kind of the thing we're talking about with replication, with creating multiple servers, is that when something fails, we can take it over, right? But doing this idea of like failover means it's just more complexity. Like distributed systems are insanely hard to do, and it's just a ton of work. But it's gonna, of course, happen with the same thing with this, with failover. So when active, right, you send heartbeats, and then if something fails, then you can swap it. And then replication is you just make multiple. So if one crashes, then you just go to the next one. Very similar, I guess, ideas. But there's master, 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 master. And this one's kind of like leader, follower, or whatever. Or, yeah, however you want to call it. Then there's nines, where we get downtimes per year. And, okay, cool. Then we get DNS servers. So how does that work? I don't know if this is too relevant for system design. But the idea behind this is that, like, he has this, like, pretty well in the mapping, right? So where does it start at? Here I need directions to google.com. So you say like, okay, google.com, you ask an ISP, your internet service providers, like DNS servers, that checks the root DNS server, which I don't even know where that's located at, but the internet machine. And then it says, oh, hey, yeah, I know where Google is. It's here. And then it talks back, and then it gets you Google's server that's running on IP address, this, which makes it very scary when you're playing Call of Duty and someone puts your IP address in chat, because that means that they know where you're located at. Typically that can't happen though unless you tell your IP address to someone or give it to like some server that's asking you. I'll just say this DNS is like super important for routing traffic. So like when we know the IP address of people that are actually contacting our website, then we can start doing things like routing them based off like servers or sending them to like places that they need to be. So if we have like a Spain server or a London server, we can keep our servers like locked, on that region essentially. Content delivery networks. So this is a very useful tool for like distributing things, right? So again, I talked just recently about regions and sending data. Like, why would we want to send a packet over from here all the way to Africa or whatever? This is not Africa, this is South America. But why would we want to send a packet from Europe all the way to Australia? Like, why not just make a base in Australia that has the data, and then we can just pull from there? So content delivery network just stores like HTML files, CSS, typically just these photos, and it just lets people grab them faster instead of sending it over, a large part. There's push CDNs and pull CDNs. Load balancers I already talked about. It's this idea of routing traffic. And again, he doesn't talk too much about it. Like, my diagram is probably better, but some other things is that there's actually algorithms. So we can do random, least loaded, sessions, and cookies, right? And when we say least loaded, it's the server that has the least amount of load, right? The least amount of people using it. So you can just route traffic based off that. You do round robin, weighted robin, all that stuff. Horizontal scaling, I talked about this. And again, he links things here too. So this is the NGNIX thing I mentioned earlier. But he lists like all these resources that you can read if you want further reading, which again would be very useful. Or you can just read Designing Data-Intensive Applications, which will get you there too. If some of these things are still like just not really clicking. Again, I'm kind of going through these. Reverse proxy is kind of like a weird load balancer. I guess that I don't even know what it really does. Centralizes internal services by providing unified interfaces to public. It forwards it. Responsive client. You get better security, better scalability, compression, caching, and static content that you can deliver. So reverse proxies feel like better versions of load balancers. More security, more caching, more compression. more flexibility, but it's harder to implement. It's just more annoying to work with. Cool. Databases. So we have SQL versus NoSQL. The king of databases right now is like relational databases, and then like DynamoDB/Cassandra. From my experience from reading online, relational databases have been around for a long time, and they make things very, very nice for, especially specifically with ACID, optimicity, consistency, isolation, durability. Right. A transaction happens, either all of it finishes or not at all. So if you have like multiple rows we're changing, again, if you don't know what a row in a database is, like you're gonna have to go back and maybe watch a YouTube video on what a database is. But essentially, if we're modifying things in a database, that like when something else is modifying those things, like things aren't gonna break, right? So we just want to make sure stuff like that doesn't happen, which is very important in distributed systems because it happens a lot that we have a lot of people reading data who really want to access Beyonce and maybe even modify like things in it, and you don't want it to break everything. And then durability, once it's committed, it will remain so. So this idea that like your data is permanent. You can access your data. If you write it to a file, you're going to see it there. And there's different types of replications you can use: master replication, leader follower, federation, sharding, which is this idea of like splitting things up. So again, very similar, right? So you have a database for the users from A to C, D to F, G to I, X to Y. Now this is partitioning. I don't think this is sharding because these are each unique databases, but sharding would be the idea of like you can do it within the rows, essentially. Then we have denormalization of databases. So this is the idea of like splitting things up in it, which again, if you don't understand SQL, then this is not going to make any sense to you at all. But let's actually look up an example of just denormalization. Again, assuming that you actually know how a SQL table looks like. If you don't, then you're going to be lost, and nothing I can do to really help you about that. What you're going to notice here, so here we have like a normalized database. So ID points to ID, like user ID, like everything's kind of like there, like everything's has like, this one only contains like first name and last name. This one only contains allocated, not allocated, right? But this one has duplicated data. So it's this idea of like duplicating data for tables or databases, and yeah, it's duplicated. Yeah, it probably slows things down, but you can reference that data faster. So this one, storage type is here, first name, last name, and now we get like some useless stuff. Like this isn't, why is this here, right? But it's there for a reason. It duplicates data, but at the cost of or at the benefit of like allowing you to do faster queries, right? Data is duplicated. And I don't know why he doesn't give the pros here, but those are the pros. It's just that you can do things better. Like you can do reads better and just faster because you can have the data already. And there's SQL tuning. You can like improve your SQL queries. That's a thing. Partition tables. We have NoSQL too. So it's like an alternative. That's actually very competitive, actually. It's called base. Again, it's kind of a useless term that means almost nothing. Basically available. What the heck does that even mean? Could you give me a number? Nope, you can't. Eventually consistent. Again, overloaded term. What does that mean? Nobody can say. Who knows? All it means though is that this is way more flexible than SQL. Way more flexible, and as a result, you can do some pretty nice things with it. You can make some pretty nice applications pretty fast with no complexity or little complexity. And then here's another one, column-based databases. So you can use these for OLAPs, so analytics. You can kind of store queries that you would do very commonly and just kind of get them immediately. And graph databases, we're going to skip these because, again, these aren't useful at all. You probably never seen them in an interview. And caching. I talked about caching too before. I kind of want to just get through this, honestly. Communication layers. Again, I don't even think this is necessary. This is like networking stuff. Like it's not in a system design interview. If you're interviewing for a networking role, maybe infrastructure, they would ask you that, maybe. But yeah, gRPC versus REST, like this stuff doesn't matter. Security doesn't matter. But then you get actual problems. So essentially, like this is it. Honestly, You know, this is like 90% of you're 90% of the way there to not being bad at system design if you understand all of these things. And you can honestly pass like system design interviews because at least the ones that I've been asked, you know, I haven't seen any crazy questions, and most of it's just kind of relying on this thing. So, all right, cool. Thanks for watching, and if you liked it, I'll make another video going over some other stuff. If not, then I'll see you later. But like, subscribe if you enjoyed it. Peace. See you. Thank you.